talk about homework answers. All right, going through kinetics homework. So looking at the first problem, we have a scenario that has a single reactant and two products. We're only paying attention to the reactant part. If you double your reactant, in this case, for instance, if you compared the 0.2 as the first line of data there with the 0.4, and then you look at the rates, the rate didn't just double, the rate actually went up by 4. What does this mean for you? It means that the exponent that goes outside your square brackets for the NOCL needs to be a squared. It needs to be a 2. Because remember, your choices are really limited to start with anyway. 0, 1, 2, 3 is pretty much it. This one ends up being a 2. I picked the top line of data to figure out what my K value was, but it shouldn't be substantially different if you picked one of the other two lines. I put in my rate, I put in my concentration, and I squared it and solved for K, which should give you 4 times 10 to the negative 8th. All right, on the one below it for number 2. This one, I gave you all of the relevant information such that you can calculate your rate value. K being 3 times 10 to the negative 4th, the ammonia concentration being 0.26, and the nitrite. And actually, I just realized when I was typing, I was typing answer keys to this, and suddenly or other, I appear to have changed by accident my subscript here. Let me see if I can fix this. It's supposed to be nitrite, not nitrate, was 0.08. All you're really doing is just multiplying your 3 values together, and that will give you a rate of 6.24 times 10 to the negative 6th. Then we have a conceptual question. What happens if you increase temperature? As a general statement, that increases your rate. For the last one on that page, note this is a second order reaction. So I need to account for my initial concentration. Your T1/2 is 1 over the K value times that initial concentration. If I plug in my numbers, 0.399 and 0.050, and finish out my math, you should get approximately 5 seconds. And the unit is seconds because when you looked at the rate constant, the time unit used there wasn't seconds. All right, then we have a data table that involves K per second, which is basically your rate, and your temperatures. So you needed to natural log your 4 K values, and you'll get numbers that are increasing 2, 3, 5, 6 with accompanying decimal places. Make sure you are adding 273 to change from Celsius to Kelvin, and then do 1 over T. All of those end up to the negative 3rd power. You could have graphed it, but truthfully, since all you're looking for at this point is a slope, I think change in Y over change in X is the most straightforward way to do it. I picked the first and last data points. If you picked 2 other data points, you might not end up with exactly the same value, but it should be fairly close. I gave you slightly imperfect data when I generated this. So my slope when I did 0.1 minus 0.4, eventually gave me, and I actually realized that my slope is negative 3.997 and over 3.4 times 10 to the negative fourth. So your slope value is fairly large, 11,755. Note that according to examples I gave you earlier, that the slope is the same as negative EA over R. One of the things this does for you is the negative slope and the negative in front of your EA cancel out, such that you have a positive value and you're dividing by the R, which has joules in it, 8.314. If you left it in joules, because actually I said determine the activation energy and I didn't specify which unit you should use. If you left it in joules, it's about 97,000 joules. If you converted it over to kilojoules, it's about 97.7 kilojoules. The last one has an easy part and a hard part. The first segment is more strictly plug and chug in that you started out with 68 grams. You're asked to find how long does it take to get all the way down to 5 grams. So start plugging this into your equation that has natural log of A0 over A and K, 0.037 in this case, times T. Divide, you get 13.6 for what was inside parentheses. If you take the natural log of that, you get 2.61. Finish your division and you get 70.5, or if you rounded it and just called it 71 minutes, that was all right. The second one is a little more complex. You're starting out with the same equation because we're still same reaction, same order of reaction. But I have an unknown. It's 68 over whatever my later value was. But I do know what my time was. My time was 25 minutes. This will give me then 0.925 on the right-hand side. In order to get rid of my natural logs so that I can find my unknown, anti-log, anti-natural log, both sides. Then divide. This gives you an X value of 26.98. But think about what it said. You want to find out how much got used up in terms of your original reactant there. So you need to subtract. You started out with 68. You had not quite 27 after those 25 minutes. That means 41 grams of it actually turned into oxygen and other substances. Divide by your molar mass, so 108. That gives you 0.38 moles. Now we got to throw a little stoichiometry in. It is a 1-to-2 ratio. If I scroll back up here so I can see my equation a little bit better. Note the original equation there said 2 N2O5s give you 2 N2O4s, but only a single oxygen. So that's why your stoichiometry has to be taken into account there. That will give you 0.19 moles. This is the one that I gave you a little hint for, in that you need the ideal gas law to finish off this problem. Put it into PV equals nRT, solve for V, and you get approximately 5 liters. So we've got 3 pieces that are all pulling together here. We've got kinetics and stoichiometry and a little gas law. So all of those pieces together had to kind of be meshed so that you can find the answer to that one. That one was definitely considered to, I wanted to consider that one to be the kind of challenge portion. Questions about this homework set? All right. Let me shut that file and find my equilibrium stuff. All right, we got through about 2/3 of the equilibrium chapter itself. So we are picking up with Le Chatelier's. It would really help if I actually shared the screen. I suddenly realized I pulled up the file and didn't hit share screen. Brain freeze. There, that's better. All right, this one is also information that corresponds with some things that I've been loading to the lab module. Mr. Wheaton generated a really decent set of short videos that are all kind of linked together that will correspond with a report sheet that is one of the remote do on your own labs. So the idea that we're kind of dealing with here is everything in equilibrium involves assuming that your forward and reverse reactions are both happening at the same time. But because they're both happening at the same time, it's possible, even not very difficult, to actually sort of unbalance the system and make forward be more in control or possibly make reverse be in control. So more notable dead guys. This one is named Le Chatelier, or his name was Le Chatelier. And the way it's stated here is if a change is imposed on the system at equilibrium, the position of the equilibrium will shift in a direction to reduce that change. All right, from a statement that's kind of a little bit vague, yes, we can say that it's going to do something to relieve the stress. All right, let me switch over to my whiteboard. All right. Party balloons. All right. Long, skinny party balloon. Okay. And we'll assume like maybe this is the end you tied it on. All right. If I take my hand and I squish on this end, all right, in comparison, ignoring the fact that I can't draw a hand on this whiteboard, what will happen is that this part will be much thinner and this end will end up being much larger afterward. Okay, think about that. You exerted stress, you squeeze the right hand end of it, and it makes the left hand end somewhat bigger in response. All right, what if as I attempt to draw a relatively straight one, okay, what if I squish on that end, okay? So this time I am exerting my stress on the opposite end. And so my left-hand end is going to be smaller because it's being stressed. And all of the air has been sort of squashed over toward the right-hand end. Okay, so this gives you at least a little bit of a really nasty looking visual for kind of thinking about what exactly are we doing when it says exerting a stress on the system. All right, let's go back to the notes. All right, in chemistry, stresses usually imply concentration, volume, temperature, or pressure. So let's look at the concept of the concentration one first. And after spring break, we're literally going to be using this particular equilibrium as part of a lab. And you also see it in the video for the Le Chateliers that's on Canvas. Iron +3 version in solution has kind of a yellowish tint to it. Okay, think back about 6 weeks. Well, maybe it's actually more like 5. It also depends on whether you're on A group or B group. We did the spectrophotometry lab that had 4 solutions, and they were iron and nickel and cobalt and copper. So the slightly yellowish one was the iron one. Now, thiocyanate is usually made from sodium thiocyanate or maybe potassium thiocyanate. But the thiocyanate itself doesn't impart any kind of a color to the solution. But when you mix them, okay, you would think that yellow and nothing should make paler yellow, okay? But in this case, because we have a coordination compound, things we saw early in the semester, you get a shade of red. It's actually kind of an orangey red color. Now, what can I do to this to make the equilibrium shift? All right, well, if I add a little more iron, think of this as sort of metaphorically taking your finger and pushing on the tube where the iron is, which is going to squish it toward the right-hand end. What you're doing is if you add more iron 3, the equilibrium thinks that there should be a specific ratio of iron to product. And so it will hastily make some more product to try to use up the extra iron. What if I add more product? What if I add more FeSCN? Well, that's kind of making it flow backward. It's going to shift to the left because it now thinks that there are too many product molecules. And so it hastily disassembles a few of them and sends them back in the direction of becoming Fe+3 and SCN. What about more indirect things? You can remove, decrease concentrations by adding things that will react with your existing molecules. So oxalate, C2O4 - 2, is something that sticks to iron. So let me hop back over to my whiteboard and get rid of all my scribbles. All right, so if we have some Fe plus 3. We add to it some oxalate, C2O4 minus 2. All right, we are going to get some Fe2 and then C2O4, of which there's 3 of them. And obviously I didn't balance this reaction as sort of going into it. All right, so I would have to go back and put a 3 here and a 2 here. But the key feature is this is a solid, okay? This is something that actually makes a precipitate. So back to my other file here. When I add the oxalate, it removes it from solution in that it sticks together and precipitates down to the bottom of the test tube. But your equilibrium thinks there ought to be some of it around. So it will shift to the left, making some of the product molecules fall apart back into iron and thiocyanate. Pressure and volume don't have a great deal of an effect on things that are aqueous or solutions. They do have a relatively large effect on equilibrium when we are talking about gases. Okay, think all the way back to Boyle's law. Okay, Boyle's law said that pressure and volume were inversely related. Okay, when you sit on the whoopee cushion, it gets flatter. Okay, so you increased pressure and decreased volume, and yes, it makes that sound. If you had a decrease in pressure, put a peep in a vacuum chamber. 'Tis the season for peeps, or tis almost the season for peeps. I noticed that the grocery store this weekend had them when I was out shopping. So if you decrease the pressure, it will increase your volume. Now, there is a variant on this where if you increase the pressure, but you did so, like maybe you added krypton, which doesn't really react with anything, and it doesn't really have anything to do with the reaction, it actually wouldn't create an effect. You actually have to think about it in terms of what are you adding, and here's another piece to the puzzle, what are your coefficients? Because coefficients, meaning how many molecules are on the left versus how many molecules are on the right, make a substantial difference. All right, N2O4 and NO2, but there's 2 molecules of NO2. If I increase my pressure on this equilibrium, is it going to shift left or right, or is it going to sit there and do nothing? Because I have 2 moles on the right and 1 mole on the left, it's going to shift left. It's going to squash some of those molecules of NO2 together into single molecules in its attempt to relieve the stress. Because remember, that's what Le Chatelier is all about. If I decreased my pressure, it would shift right because it's going to expand to make more moles, or you could view it as more molecules. We can treat equilibrium equations as if we were talking about single molecules, or we can treat them as if we're talking about full moles. It doesn't actually change the theory behind it. Now, the Ks that we've been seeing, in this case, capital Ks, KCs and KPs for this chapter: pressure, volume, concentration. None of those actually change your K values. They might change your equilibrium concentrations, but they're not actually going to change the K. If you want to change the K, you also have to change the temperature. Now, what if your reaction happens to be endothermic or exothermic? And in this case, I picked one that was an endothermic reaction. We have some more coordination compounds. We've got cobalt stuck to 4 atoms of chlorine and some water. If you let this go to equilibrium, you will get some hydrated, not really hydrated, aqua ligands attached to your cobalt, and you get some Cl minuses that are floating free. But this is a reaction that is, as written, exothermic. Okay, it produces a little heat as a byproduct as it is going from left to right. And I found a cool little picture to kind of give you a visual for this. Cobalt chloride is kind of a pinkish purple shade. The cobalt with the ligands of water is, and actually, I just realized I literally cut and pasted this from a website, and it says solution after heating. And at least to my little eyeballs, the one on the right-hand side there with the little lit Bunsen burner underneath it is blue. Oh, actually, never mind. Okay. Yeah, it's been kind of an odd day. You're adding heat, which is driving it backwards. Basically, you are inputting something that the equilibrium views as a product, which is shoving your equilibrium backward. And yes, that's why it turns blue. For a moment there, I'm just like, wait a minute, it's backwards. But no, it isn't, actually isn't. If I turned off the Bunsen burner and let it cool back down, it would shift to the right again and return to that sort of pinkish purple color. Basically, what it's doing is it's sort of trying to rewarm itself. So this gives us a couple of generalities we can use. We can say that if you would like exothermic reactions to kind of do their thing and produce more products, keep them cool, decrease their temperatures, kind of like your radiator. Okay, if you want your car to not overheat, you obviously want your radiator to be functional and absorb the heat from the engine into its liquids and all that sort of thing. If you want to favor an endothermic reaction, endothermic reactions are usually kind of sluggish. You've got to kickstart them. In this case, kickstarting them by adding temperature or by warming them up is going to give you a better endothermic reaction. Keeping in mind that from a thermodynamic point of view, The ones that are listed as being positive delta H's are the endothermic ones, and the ones that are given the sign of negative for the delta H are the exothermic ones. That brings up one last bit, okay? Catalysts. Now, we saw catalysts in the last chapter. We saw it in that your kinetics will give you faster rates based upon adding the catalyst, which tends to make people think, ooh, well, that means it's going to go forward. No. For an equilibrium reaction, it actually speeds it up in both directions. Because if it lowers your activation energy, which is basically the purpose of a catalyst, it's going to lower the hump, which translates to lowering the hump going in both directions. You have an easier way of making it go forward because the hump is not as big, but you also have it equally a bit easier going backward because, again, it's all about that activation energy. If you lower it, it is going to give you basically the same directions, or both directions are going to proceed better. So it doesn't give you a shift left. It doesn't give you a shift right. It makes them both speed up in opposite directions. So they kind of null each other out. All right, and that is the end of the equilibrium chapter. Questions about the material before I talk a little bit about the homework set? All right, let me shut this file and find the homework. Which would probably help if I actually looked in the right folder. I haven't got everything all swapped around between folders yet. It's got to be a folder with this in it. There. Back to screen sharing. All right, this is what the equilibrium homework looks like. Remember, I tipped you off last week. Equilibrium homework is due Thursday night. So I gave you some information and asked you to calculate Kp. I gave you a reaction and asked you to write the equilibrium expression. There's no math for that one. For number 3, I gave you a relatively straightforward note. It's moles in 1 liter. Tip. This means we're dealing in terms of molarity. And you should be able to do a standard ice chart for this. For number 4, you have Kc, but I ask you to find partial pressures. So clue in starting this one is going to be convert your Kc to a Kp before you do your ice chart. Oops, I think I scrolled down too far. No, actually I didn't. All right. Then I threw some Le Chatelier stuff here in on number 6 and one of the concept questions for the last one. So usage of ice charts is a key feature to doing the equilibrium homework for this chapter. Questions?
I missed it. I'm sorry. Did you say it was due tonight or Thursday night?
Thursday.
Okay.
We finished the chapter tonight, therefore it's due the next class day, so by midnight on Thursday. That way it gives everybody a chance to go through the stuff that we covered today. I finally got all the stuff covered or loaded for the rate law lab. Let me see if I can get Canvas to let me swap to the other portion because I want to talk about that a little bit. And of course, it immediately tries to log me out. Hang on. I swear, Canvas has just got to be like the most biggest disaster of most things. All right. Let me share it. Okay. So this is your interface for lab. So some of you did molar mass of a solid last week. Some of you do it tomorrow, but there is one more lab that is part of the sort of pre spring break version here. So let me pull open the rate law one. All right. I got my video to work. Okay. It's about 3 minutes long or something. So watch the video just so you know what reaction we're actually dealing with. This is a very math heavy lab. If you have looked at all at the report pages that are in your lab book, you will see that they give you basically 3 pages. It's a back and a front, a back, and then there's another page, which we're actually not going to use the 3rd page at all. We're using this thing called an iodine clock here that we're actually shorthanding a little bit. So if you look at the reaction here, we've got iodine and peroxide, and H3O plus is known as hydronium, something that we're going to cover in greater depth with the next chapter. And we get triiodide, which is this oddball molecule that actually gets picked on a lot when we talk about molecular geometry, that has a single minus charge on it and some water as a byproduct. As in most of the kinetics, we really aren't paying much attention to the product side other than the fact that when it happens, you get a color change. We're also simplifying this a little bit in that if I write my rate law, it's going to really only have 2 reactants. We're using or utilizing a buffer system, which means that your H3O plus concentrations actually aren't changing. So we're going to simplify it down to rate equals K, iodide to an exponent, peroxide to an exponent. When you read the recipe chart that is 2 pages back from the report, you indicate what the concentrations are, just make them match the information in the recipe chart. So here is your data. There are 8 columns on the report page. You can leave the 8th one blank. Your time, basically the time it takes for it to change color. Utilize this data, 89 down through 138. Then it will ask you to calculate such things as how many moles of thiosulfate. So you need to look at the recipe chart, figure out how many liters, because the recipe chart's in milliliters. You're going to have to move your decimal place. And 0.02 molar. Multiply those two together, the liters cancel out, you get moles. The moles of triiodide is half the moles of thiosulfate. For your rates, take your triiodide concentration moles and divide by seconds. These are not natural logs. If you look at the data page there, you'll see that they all say log. So make sure that you are using the log base 10 on your calculator to do this. So just take the log of the previous line. For volume, again, this is a read the recipe chart thing, seven different values there. To do your iodide concentration, this is a little bit of a dilution problem because we're going to take liters of Ki, make sure you move your decimal place, multiply it by 0.3 molar. And because if you actually read horizontally across your recipe chart, you would notice that the volume of everything once it's all added together is 10 mils. So we're going to divide that value there by 0.010 because that's 10 mils in liters and log that one. When you do all of those things, and actually I probably should have said you do basically the exact same thing for your peroxide. I just suddenly realized I skipped the line that said do the same thing for peroxides. I'll go back and fix that. We talked a little bit before about theoretical versus applicable, or theoretical versus useful versions. So rate equals K prime iodide plus C. Okay, that's the theoretical version. What you're going to do is create a graph. Okay, there's a little mini picture of the graph on page 276. Create a graph from only 4 of the 7 data points. Trials 1, 2, 3, and 4. Do a trend line. Your whole number, whatever closest, because remember your choices are 0, 1, 2, 3. That's it. So it's whatever one that's closest to becomes your p-value. Your line 7 values are the x-axis, the line 4 values are the y-axis, just to kind of make sure you're doing this on the right. This is a third quadrant graph, okay? This means you're going to get negatives and negatives, okay? When you do the second graph, this is 2 separate graphs. Make sure you do not try to put all 7 points on one graph. It will really hose your data. Use point number 1 again, and then points 5, 6, and 7. This time you're graphing for the peroxide slope. Once you find your 2 values, value for P, value for Q, go back, and this is on the back of the page, okay? Put in the values into your rate law, solve for K prime. I will also tip you off. They're all relatively small values. Average them. And this is one of the very, very few reports we're actually going to pay a little bit of attention to standard deviations. Google it. Okay. There's a ton, especially if you're not familiar with how to do standard deviation and relative standard deviation. There's lots of websites where you just put your 7 data points in and say, you hit the button that says standard deviation, and it tells you what the value is. Okay. I don't need to see your math. Okay, you can use a website to do this. Also do the same thing for the relative standard deviation. Okay. We are not doing the activation energy portion. That's not a super valuable or easy thing to do in terms of the way you acquire the data. So we usually only do up through basically about the 2/3 of the back of the report page and skip the whole page that says activation energy. So all of this I like because it does give you nice real-ish data. I really wish we could actually do these for real. It's kind of a cool little reaction. It has this neat little visual where it changes color, and you time it, and none of them take a really super long time. Even the one that I taped on the video takes maybe 3 minutes. So most of it involves pipetting and lining up all of your little flasks and everything, and then pouring everything together and hitting the timer and acquiring your data that way. But the best we can do right at the moment is give you a video and some data and let you crunch the rest of it. So questions about that lab? I like that lab in that it does fit nicely with the information that we've covered in the kinetics chapter. All right, so Thursday, we'll start a little bit of the acid-base equilibrium. I can't remember if I actually loaded that to Canvas yet or not. I will if I haven't. And your homework for equilibrium is due. Basically, what this should give you is only lab stuff to work on over spring break. Okay, because a whole bunch of you owe me a bunch of labs. Okay, and labs are very time consuming in terms of doing all the number crunching and all of that. So if you have whatever you haven't turned in for lab stuff, my advice is over spring break when we have the classes, is focus on your lab reports and pre-labs so that you can either turn them in digitally or you can send or give them to me the next time you see me actually physically in lab. And that will hopefully get everybody a little bit more caught up on all of that end of it. Questions? Otherwise, I will see you on Thursday. Some of you I will see tomorrow night, though. Some of you I will see in lab tomorrow night. And everybody else I will see on Thursday.